In this video, we shall talk about the resonance phenomena in AC circuits. Let's look at the following AC circuit. The circuit consists of a resistor with a resistance R, inductor with inductance L, and capacitor with capacitance C connected in series across an AC source. This AC source has a constant voltage amplitude, let's call it V, with variable frequency, or rather angular frequency, omega. The instantaneous current is labeled with little I. We know the resistor has a resistance R and this is constant. The inductor has an inductive reactance X sub L, and this is a function of that angular frequency, and it can be expressed in the following manner: angular frequency times the inductance of that inductor. The capacitor has the capacitive reactance, and that is given by 1 over angular frequency times the capacitance of the capacitor. And we know the impedance in the circuit is expressed in the following manner, namely XL minus XC squared plus R squared square root. What that means is, in terms of angular frequency, it is omega L minus 1 over omega C squared plus R squared. The current amplitude I can be related to the impedance of the circuit and the voltage amplitude of that source, and it can be written in the following manner, namely the voltage amplitude of the source divided by the impedance of the circuit. We see that as we vary the angular frequency, X sub L and X sub C will also change. The changes of these two quantities would directly impact the value of impedance. That means that would also impact the value of that current amplitude. So what we have here is the current amplitude is also a function of that omega. The maximum value of I occurs when the impedance is minimum. And from this expression, the minimum value of impedance occurs when the quantity in the bracket vanishes, namely when the inductive reactance equals the capacitive reactance. Let's assume it occurs at a specific frequency. Let's call it omega naught. So what is the value of omega naught? Omega naught L equals 1 over omega naught C. That means omega naught is 1 over square root LC. So this is what we called as the resonance frequency of the circuit. You see, when omega equals omega naught, this term will go to 0 and Z equals simply 2R. When that happens, the current amplitude in the circuit is maximum. It must be noted that the resonant frequency is controlled by two quantities: the inductance of the inductor in the circuit and capacitance of the capacitor in the circuit. So at the resonant frequency, the current amplitude is quite simply the voltage amplitude of the source over the resistance of that resistor in the circuit. Let's plot I in ampere versus frequency, or the angular frequency, in radian per second. Let's assume that the resonance frequency is right there. So the value of I peaks at omega equals to that resonant frequency. So the curve would look something like this. Like that. Assume that we are plotting the curve for a value of R of 500 ohms. What would the curve look like if I were to plot the graph for resistance value of, let's say, 2000 ohms? So this is larger, so the peak would be more suppressed. So for 2000 ohms, the curve would look something like that. So that is the curve for 2000 ohms. What about, say, for 200 ohms? In this case, the peak would be higher. say like that. And this corresponds to 200 ohms. Now keep in mind that these sketches are not up to scale. The aim of this curve is just to exhibit the effect of resonance in an AC circuit. Let's look at this problem. The LRC series circuit shown below is connected to an AC source with constant RMS terminal voltage of 1.2 volts and a variable frequency. What is the resonance frequency? Let's do that first. Now we have seen that the resonant angular frequency is given by 1 over square root the value of the inductance times the value of the capacitance. Now in this case, the value of inductance is 0.5 millihenry. So 0.5 times 10 to the power minus 3 Henry. Capacitance is 110 picofarad. So 110 times 10 to the power minus 12. And that's going to give you 4.26 times 10 to the power 6 radiant per second. The resonance frequency in hertz is that omega naught over 2 pi. Let's call this F naught, which is 678 times 10 to the power 3 hertz. Or quite simply 678 kilohertz. Part B. Find the inductive reactance and capacitive reactance at the resonance frequency. So the inductive reactance is omega naught times L. So omega naught is 4.26 times 10 to the power 6 radian per second. L, the inductance value, is 0.5 times 10 to the power minus 3. And that's going to give you 2,130 ohms. Now the capacitive reactant. We know at resonance frequency, it is quite simply the same as the inductive reactance. So it should also be 2,130 ohms. Part C. What is the reactance and an impedance at the resonance frequency? Reactance of the circuit is quite simply XL minus XC. At resonance frequency, they are identical as shown by the answers in Part B. So that comes to 0 ohms. We have shown the impedance at resonance. It's quite simply the value of the resistance. And in this case, it's 550 ohms. Now Part D. What is the RMS current, the root mean square current, at resonance? So the root mean square current at resonance is the root mean square terminal voltage over impedance, but impedance equals the resistance. So capital V is given to be 1.2 volts in the problem, and R is 550 ohms, and that's going to be 2.182 times 10 to the power minus 3 ampere, or quite simply 2.182 milliampere. Now let's do part E. Calculate the RMS voltage across L, R, and C. The RMS voltage or potential difference across the resistor equals I times the resistance. Now I is that, so 2.182 times 10 to the power minus 3 ampere. R is 550 ohms, and that turns out to be 1.2 volts. The RMS voltage across the inductor equals the current amplitude times the inductive reactance. Note we are doing this for this frequency here. I is 2.182 milliampere, X sub L is 2130 ohms. Multiplying them, you get about 4.65 volts. The RMS voltage across the capacitor is given by capital I times the capacitive reactance of the capacitor. So I is again given by that, and X sub C is again 2130, and that will give you the same answer as that for the inductor, 4.65 volts. And we see the RMS potential difference across the inductor-capacitor combination is given by I times the reactance of the circuit. Since the reactance of the circuit is 0, then the potential difference across the combination is also 0. We are dealing with an AC circuit, so the potential difference, that one, and the potential difference across the capacitor are 180 degrees out of phase, so they cancel each other, giving us a value of 0. That solves the problem. Thank you for watching.